Hello and welcome everybody. Welcome to Automotive World. I'm Martin Carl. I'll be moderating today's webinar, which is all about functional safety. To talk us through this topic, we're joined by Roman Isola from Elektrobit, who will discuss how to optimize the integration of functional safety requirements within an electronic control unit project. Functional safety is one of the key technologies in today's automotive industry, and safety systems must work reliably to ensure driver, occupant, and road user safety, even in the case of a malfunction. One of Elektrobit's core competencies is providing industry-leading software solutions for safety-related ECUs. And so, as I said, we've got Roman Isola from Elektrobit with us today. He's product manager for Classic AUTOSAR at Elektrobit, and he will be outlining how EB's product portfolio can be used to implement safety requirements within an ECU project, including EB's Classic AUTOSAR offer for projects with safety requirements. We'll also be looking at AUTOSAR safety architecture. The format will be a presentation followed by a Q&A. If you'd like to ask a question, please type it into the Q&A box on your screen, and I'll put those questions to Roman in the time that remains available. And there'll be slides and a recording of the available that you can access afterwards, and we'll send you an email to let you know how and when you can get hold of those. So that's all you'll hear from me. I'm going to hand over to Roman now for functional safety projects with safety requirements. Roman, the floor is yours.
Martin, for the introduction. So yeah, welcome everybody to the webinar today. We want to talk about functional safety in an AUTOSAR environment. In this case, we talk about a short introduction into functional safety, what it means, also the requirements, then hop over to our products and see how to utilize EB's products in a classic AUTOSAR environment, and then we talk a little bit about the architecture and how to use and achieve functional safety. Okay, so let's jump into the functional safety introduction. So we just had the agenda. So here we first should look at the definition, what functional safety means, and the first source here is Wikipedia, and Wikipedia says the objective of functional safety is the freedom from unacceptable risks and physical injury or damage to health of people, or either directly or indirectly. So here it is clearly stated, so it is the freedom from an unacceptable risk. The question here actually is what is unacceptable in that term. So if we look further, we can have a look at the functional safety ISO standard, the ISO 26262. And here it is a little bit more precise. It says the functional safety is the absence of unreasonable risk due to hazards caused by malfunctioning behavior of EE systems. So, and they define further that an unreasonable risk is a risk which is unacceptable in with the social moral concepts what are currently available. So that means already that this might change over time. So what was acceptable a few years ago might not be acceptable in a couple of years down the road. So here we already have some variance. If we look at the term risk, it basically is defined as the probability of the occurrence of harm and the severity of that harm. So the severity then is more defined as the extent of harm which happens in this potential hazardous situation. And yeah, with that, it comes back to the hazard situation, and so what is a hazard which could occur and lead to an unreasonable risk. And yeah, here we have the definition based again on the source of harm and the malfunctioning behavior. And I think that is a really important point here. With the malfunctioning behavior means that we have an unintended or failure behavior. So it is basically a behavior which is not expected, and so the system does not work to its design intent. So that brings us to the functional safety within our software development, especially around AUTOSAR. So it comes down to the analysis of the hazards and the risk management. And if we look at software faults in general, they are always systematic. And with that, that means they will occur. So there is no aging or any other effect in software. So if there is a functionality in software, it is in there from the beginning. So we cannot determine the occurrence with statistical methods. So we cannot say, okay, software will fail over time in 5% of the cases. So we need to assume that a software fault will occur, and to actually change that or to control that, we need to have mitigation strategies, and to get to these, we need to look and analyze the whole system. That means we are not only looking at a certain function within the system, we need to have a look on the whole system. So, and based on, and to handle basically these risks which are identified during the analysis, there needs to be a proper risk management within your software development. That means to keep your risk as low as reasonable practical, so the Arlo principle. And here we have a good source for our requirements to handle such risks, and it has influence on our system design, which means based on our analyses and the requirements we identify, we need to design our system around these risks to control their occurrence. So that brings us to a little summary. So the most important part, and I cannot stress that enough, is that safety is always a system property. So it is always the whole system which needs to be analyzed, the whole vehicle in our case usually, the high-level function which actually causes the issue, and it should have an end-to-end scope. For software in particular, it actually brings in the topic and the task of risk management mainly. So it is a system design or functional safety requirement management and risk management, which are necessary to be handled within your software project. And and the ISO kind of determines the classification of safety into automotive safety integrity levels, the so-called ASIL levels A to D, which define the severity of your malfunction or of your system itself. Okay, so we just learned basically that risks and requirements especially are key in a safety project. And so that brings us to the point to talk a little bit more about functional safety requirements, how to get to functional safety requirements, and how to manage them, and which artifacts will arise from there. So to get to your functional safety requirements and also your functional requirements, you usually start with a functional feature definition, high-level feature definition, and your safety goal. out of these two inputs, you derive, on the one hand, functional requirements, and on the other hand, you have functional safety requirements. Basically, these two have influence on your hardware design, so that defines which microcontroller you should use, what kind of redundancy should be built in. And out of these functional safety requirements, high-level functional safety requirements and functional requirements, you can derive further more technical software safety requirements and also your functional software technical requirements. And on this level, basically, you can already map them to a software design, software architecture, and here the term of software safety element out of context comes into play. So you can buy a off-the-shelf product where you can map your functional safety requirements on and have them basically fulfilled with an off-the-shelf product. So that brings us to the well-known V model. So I just said that the safety goal has an influence on my high-level functional safety requirement, my top-level functional safety requirements, and based on this, I have on the system requirements level, I derive from my safety goal, I derive top-level safety requirements from that. Further down, on the system architectural level, I create a functional safety concept, or even further down, a technical safety concept, and specifically on my technical challenges. For the software requirements in the end, I end up with technical software safety requirements, and from here, I'm basically handling all of these requirements, so they coexist with my normal functional requirements. And that is the important part on the downside, or on the way down the V, where we have our software architectural design, which has nothing special between my normal function and my safety measures I take. That means I take care of my technical safety requirements in a normal way. I would also do functional requirements. So there is no safety architecture design or anything, or that should not be necessary. In that case, you should be able to just do normal quality safety or software development based on a set of requirements. On the verification side then, upwards the V on the right side, there's also not much special, but you need to basically verify your safety mechanisms on the different levels, on the software level, on the system level, where you can determine if your functional safety measures are actually working. Okay, so how do I get to the functional safety requirements, the technical functional safety requirements, and what should be the content of them? So what do I need to look at in the case of I have a safety goal or safety features in my ECU. So input for the requirements are the higher levels. So on the system architectural level, where we have our functional safety concept, our system design, and our technical safety concept. From there, I derive my safety requirements, and they should actually address things like my system and hardware configuration, my timing constraints, so worst case execution times, things like that, My external interfaces, of course, where needs to be communication, how do I interact with my environment, and the system operating mode means that I also have to consider my safe state or other system operation modes. Okay, so that brings us to the term freedom from interference. So we'll look later on basically how do I get to the argument from freedom from interference, but here I want to introduce that. And actually that this is a method where I can basically separate my safety functionality from the environment to make sure that it is not, that there's no interference between a non-safety part and something which controls the safety system or a monitor. So to assure that I can basically separate it, I have shared resources basically are only accessible for a partition for a certain function. I need to basically separate functions from each other. I need to separate monitors from functions which do the monitoring then on these functions. And I have basically I have an easier life if I apply the freedom from interference concept on the highest level possible. Okay. That brings us to the three disciplines where I can apply freedom from interference. And there we have the spatial domain where the memory protection comes into play. So here I really have a memory separation to prevent unintended writing to a system which needs to be protected. I have the temporal domain. That's basically my CPU time protection. Here I do monitor the execution time I have on the processor where my software runs, so it doesn't overrun, it doesn't stuck in a endless loop, something like that. And I have my communication data protection domain where I need to protect the information, so the interfaces which basically bring that in and out, information in and out to my software function which has a safety impact. Okay, and with this freedom from interference argument, that brings in also the EB products, because this is where I can use, so if I bring down my requirements to that freedom from interference, so if I have a requirement in the end for freedom from interference, I can use safety elements out of context. And here I would like to go a little bit into our product portfolio, what we offer to show or to implement freedom from interference within these three domains, so spatial, temporal, and data. Okay, so the first one will be the EB tresos safety time E protection module. So the time E protection in an AUTOSAR stack actually replaces the watchdog manager and the watchdog interface, and provides a safe way to do a live supervision, control flow monitoring, and deadline monitoring. So here we cover a whole domain out of that spatial, temporal, and data domains. Here we do cover the temporal domain. So the key features are, like I said, so the live supervision, the deadline monitoring, flow control monitoring, and basically what our product brings with is a smooth error reaction. Means that I can change the error reaction. So if I have a single fault, I can basically do do a reset or try it again, and don't have the worst case to do a reset actually. And so from an architectural standpoint, we see here the time E module is directly interfering with the watchdog driver and exists in its own partition or own domain, and has an interface with the surrounding environment, application environment, by checkpoints. So you can define checkpoints, and based on these checkpoints, you can then define rules on temporal flow control, live supervision, monitoring. The next product will be the operating system. Here we are in the spatial domain. So the tresos Safety OS is actually providing the mechanism for the memory protection. So it's built as a microkernel operating system. It is highly optimized on the usage for the hardware, mostly the MPU, and it actually takes control over the memory protection unit and is basically controlling the context switches between different partitions. So it is, of course, available on multiple platforms. So we talk about the well-known silicon vendors here. It has a couple of key principles during its design and implementation phase, and that basically makes the product usable, or even better usable in a safety element, as a safety element out of context, because it is kept as simple as possible. It is a microkernel which is really small and slim, which gave us the opportunity to get a certification on this part of the OS. It is robust, and it actually brings all the features the normal AUTOSAR operating system is providing as well. On the memory protection support, I mentioned it before, the OS is actually taking the full control over the MPU and is doing the switching of regions automatically during the execution, and it is using all of what the hardware is offering to provide that service to the user and the application in that case. Okay, the next product, which kind of goes along with the operating system, is the tresos Safety RTE. This also covers the domain of the spatial freedom from interference. Here we have a standard AUTOSAR RTE, which implements the RTE partitioning concept, which is defined in AUTOSAR as well. And to do a verification on the RTE, here there's two methods used. So there's the RTE code verifier, which actually is an online test, so it generates test code, which then with the current configuration needs to be executed on the target to verify that the function is working correct. And the second path is the RTE code checker and the safety manual, which actually is a tool to verify the generated code. And the safety manual, of course, gives you also certain requirements which need to be fulfilled, certain reviews need to be done to verify the generated RTE code, which then later runs in your software. Okay, and then last but not least, we have the data domain, where we have the safety E2E protection module. So the end-to-end protection is implemented as a RTE transformer, or actually a transformer module, which kind of resides within the RTE. So it is transparent for the software component to use the communication path. So we have different use cases identified, which is a normal signal-based communication. So your software component is sending or receiving your signal data on any bus, and is just calling RTE read, RTE write. The same actually works as well on some IP communication or service-based communication, which means you can basically also do your the new way of communication based on some IP. We also provide different profiles. So there's one more slide coming up. So AUTOSAR defines 7 profiles, which are designed for different communication methods: CAN, FlexRay, CAN-FD, and Ethernet. Here I have an example for the profile 4, and this is where they actually differ from each other. The location of the checksum, the location of the counter, the size of the checksum. So these are optimized for the different communication buses, depending on CAN or CAN-FD, Ethernet, depending on the bandwidth which is available. Actually, the profile is usually something which is also a system property, so it's usually chosen by the OEM because that needs to be equal between all communication partners, of course. So that is a global requirement, usually coming from also the system level. Okay, and then we have one additional product which is fairly new, but makes it nevertheless attractive. So it is the so-called EB tresos AutoCore ASIL-B ready package. This is a safety argumentation, not purely relying on the safety product, so they still play a major role here. It's concentrating on the spatial domain, and it is a process argumentation based on quality and the development process of the basic software in this case. So the use cases, either you have not the possibility, that's the upper picture we see here, you don't have the possibility to implement a partitioning concept because you don't have memory protection available on the chosen hardware, for example. Or, and that's the lower example, you have the possibility to use a memory protection, but for different reasons, be it performance reasons, you need to run your basic software in the same partition as your software, your functional software is executed. And to do this argumentation, we provide additional documentation, especially for RTE and OS. There's an application guideline how to use the standard AUTOSAR products from Elektrobit, how to configure them, what needs to be reviewed if you use them in a safety environment. And you get some evidence documentation for the quality which is provided with the standard product for the whole basic software. Means that is the quality statement actually, which states what quality level is reached with the product, and in addition to that, the measures and the results are documented within the quality and metrics report, which is evidence for the development process. Actually all I just said. Basically, the argumentation here is based on a non-interference argumentation. That means the basic software is not guaranteeing 100% functionality. So there is influence from the QM software parts also on the BSW, and if there is some wrong interaction, it could have influence also on your safety data. But so the non-interference is actually an argumentation which kind of points at the that the software is not corrupting your safety application, so your software component which has assigned safety requirements. This argumentation is actually just focusing on freedom from interference for memory, or non-interference for memory, to actually make the timing domain and the data domain safe, right? You still would use an end-to-end protection module or the time E module to do your timing supervision. Okay, and that already brings us to the last topic for today. That's the safety architecture with EB tresos. And here I would like to basically point out the EGAS concept introduced by Bosch a couple of years back. So Bosch defined in that case 3 different layers of diagnostics. So we have parameter diagnostics on the signal level. We have signal diagnostics and functional diagnostics to actually monitor your inputs and the functional execution of your software. And then there is system diagnostics on an integrity level, so you basically monitor your whole system, or the system environment, let's say that way. And yeah, basically that brings in the requirement to separate all of these monitors from each other. So the monitors and the function needs to be separated, and the different levels need to be separated. And to realize that, we come to we have the consequence that the freedom from interference needs to be guaranteed. So I mentioned before, right, when I was talking about the freedom from interference, that yeah, you somehow need to come to a system design, a system architecture, which brings in the freedom from interference requirement, and then this requirement can be addressed by the safety elements out of context. So if you apply the EGAS concept to your system design, you have basically already a pre-made path to come to the requirement from freedom from interference. And as yeah, a recommendation, the design approach should be keep it simple. I have on one of the earlier slides, right? The definition of a safe system is a system where you know what it does. So if you keep the complexity low on your system, it is easier to handle and also to manage your requirements and also manage the risks associated with that. Okay, and that brings me to my final slide for today. So the summary, it's basically the marketing sales pitch here. So what we offer, we have scalable solutions for QM up to ASIL BED, single core, multi-core systems. It is possible to mix safety and QM software within the same system or software system. The Safety OS provides read and execution protection in single and multi-core, and basically our systems are already used widely in the field, so we have also a proven in use with our products in this case. All right, then. Thank you for the attention, and I will hand over to Martin.
Thanks very much, Roman. Plenty to get our heads around there. If anybody would like to ask a question to follow up what was delivered in the presentation there, or if you have something to follow on from that, please do use the Q&A box on your screen, type your question in there, and we'll put those questions to Roman in the time that we have available to us. Can you please, well, the first question here, are there any safety guidelines or expectations that you can provide on the application of SWC development?
Actually, there are no guidelines with what the product offers with the safety product. So EBE tresos safety products, they come with a safety manual as a safety element out of context, which actually lines out a couple of extra requirements, and for the development of your software component, there's actually no real guidelines from Elektrobit which influences the process of developing those.
Okay, and so how do you protect functionality then, particularly in the ASIL-B ready package?
So basically, the ASIL-B ready package, the basic software does not guarantee the functionality. It actually does, focus on the non-interference. So there is no guarantee that there is no other corruption of data within the basic software. But it will, and that is the guarantee and the argumentation, the basic software and also the software function needs to fulfill that, which is basically then QM level, needs to fulfill also the non-interference. It actually guarantees that the basic software is not corrupting data which is owned and handled within the safety component.
All right. Well, there's possibly a good follow-on question to that has come in from somebody who's. They're quite a long question, so I'll read this out to you and then hand over. So, during safety testing, what actual difference in ASIL level or ASIL level, as per hardware point of view, is there for functional safety testing? For example, testing ASIL A and B doesn't require a hardware port for safety testing, but ASIL C and D do require a hardware port for testing.
Okay. Can you repeat the beginning of the question? Sorry.
Yeah. So during safety testing, what is the difference in ASIL level from a hardware perspective when it comes to functional safety testing?
Okay, that's a really tough question because I only know software. For hardware, I think it depends on the components you use, right? You need to build up your safety case in the same way as you would do it for software. So, but in hardware, you have specific requirements towards your microcontroller, right? The fit rates you use of the components you have, and from a testing perspective, I think there is recommendations in the ISO how to test, but that should be in the hardware part, which I'm not familiar with.
All right, thank you. I mean, this follows on again from, you did mention about hardware versus software there, but why do some OEMs want hardware safety testing for ASIL-B? And perhaps you can answer the same question regarding software.
So, I mean, for software, there's no way around testing, right? You need to do verification on all different levels. Software integration, software tests, system integration tests. That is mandatory, but that is also something you should have already if you have a proper SPICE process established in your organization. That's something you already doing, basically. So there's nothing special to do for safety in terms of testing. Of course, you need to test your safety requirements in the same way as you test your functional requirements.
All right, there's a range of questions here, so I don't think I'm going to be able to group these. I'll just put them to you one by one as they've come in. The
Okay.
EB Auto Core, can it coexist in an ASIL-D memory partition?
Actually, yes. So the Auto Core, this is our generic product. It can coexist in a partition, which is not. Yeah, actually, yeah. No, now I get the question. No, it does not. Right now. It's not able to coexist in the same partition as the ASIL-D software component. At the moment, this is what I mentioned with the ASIL-B ready package. So B like Bravo. But for ASIL-D like Delta, we're working on that, but this is not yet available.
Okay, and would this solution support self-driving redundant systems, and do you support homogeneous redundancy?
So yes, it can be used. That is, yeah, it depends on the architecture, right? If you do have redundant systems, so if you have multiple microcontrollers as redundancy, you can execute software in both micros. If you have multiple cores, you can do redundancy within the cores. Of course, there the argumentation is a little bit weaker than if you have really two different hardware modules. But yeah, that would be possible, I would say.
Thank you. How would you provide safety to QM modules and safety modules, both of which are in a cascade?
So a QM module actually we should have no safety functionality. So that's per definition, right? You cannot make or you cannot upgrade QM to safety. So if you have a safety functionality which is implemented according to a normal development process, but you don't have a specific argumentation for your safety requirements, it's not possible. What you can do is, right, there is the decomposition. So you can make a large system or a bigger system, break it down into smaller pieces, and make it more handleable. So that's going into the direction of keep it simple. But yeah, so if you have yeah, you need to find your argumentation, right? If you have so if we talk about the ASIL-B ready package, where we have technically QM software residing in the same partition as a safety system, there you need to find an argumentation. And so here our argumentation is the non-interference, which means that there is no there's no data corruption caused by the QM part to the safety part. That would be the same for the application. So if you have a QM application residing in the same partition, in the same memory context or memory space as your safety functionality, you need to make sure that there's a non-interference. And for the higher ASILs, C and D, I think there's no way around using memory protection.
Somebody's pointed out that on slide 9 you've listed FSR and normal functional requirements separately, and they've asked whether this means that safety requirements are not part of functional requirements.
No, actually, so functional safety requirements and functional requirements are coexisting, basically. But it's more like in the direction of, so it's normal requirements. They need to basically follow the same rules. But they have a different origin. They're kind of derived out of the safety goal.
And Another question, must SE00C element be developed according to QM level?
Safety element out of context, actually.
Okay, it looks like 00, sorry.
Yeah, okay. So safety element out of context actually is developed, and that depends on what is the target, our safety element out of context product. So the OS, TIME, E2E, and RTE are developed according to the assumption of ASIL-D. So that should basically cover the whole range of integrity levels. So it needs to be developed according to your safety process. So the normal QM measures are not sufficient.
All right, we've got a question here about three-layer monitoring. Can you provide a specific example for three-layer monitoring, signal, function, and system?
Okay, tough question.
Okay.
Actually, so if you have on the signal level, you would basically do a multi-input, right? So you have digital input, and you would read. You have basically two digital inputs and would compare them, for example. On the functional level, you would basically have some kind of monitoring function where you either calculate a range, check, something like that within your functionality. And on system level, basically would be a timing monitor, right? Execution time monitoring, where you do do deadline monitoring, right? So that you have a maximum execution time budget.
Thanks. Is any of your EB tool does any of your EB tool feature? Sorry, I'm not sure I understand the question. Whether your EB tool features the ability to find ASIL A, B, C, D of a software. Does that make sense? I'm not sure I understand the wording of the question.
No, actually, I'm not sure what the question would be in that case.
Okay, perhaps the person who sent in that question can rephrase that, and we'll put that to you if it comes back in. In one of your slides, you explained a mix type of both QM and safety. Can you explain this concept with the help of application requirements? Because the person who sent the question says that, according to their understanding, QM has no safety requirement.
Right. That's correct, right? So you would not address the safety and the integrity level is assigned to the requirements. Actually, not on the function, right? So, and if the software part which implements this requirement, it actually inherits this integrity level, and so the QM parts would actually not fulfill requirements which have an ASIL rating assigned to. So it is just for inherited reasons, right? You need to take certain measures, and that is the freedom from interference. So if I have functionality on a ECU which has influence on or has safety requirements, has influence on a system feature which is safety relevant. It could still have also or implement features which do not have a safety implication. And if you would not take certain measures like the freedom from interference requirements, the function which is not fulfilling safety requirements do not would actually, but if they would be able to influence the functionality with the safety implication, they would inherit the process or the measures which need to be taken to make it safe. So it needs to be, you need to do a code review or a code inspection and take certain measures to do extensive testing. And basically to still have both systems coexist on the same system, you take these measures for freedom from interference to separate QM from ASIL components, basically. So that understanding is correct, right? So they should not coexist in the same context.
Okay, and we had a clarification of that earlier question. During unit testing, is there any EB tool that also checks for functional safety requirements such as memory protection?
Oh, okay. Now I get it. Okay. No, there's not. We don't have a tool. So basically, I assume for the application, and there's no such testing. But actually, I mean, if you would do, I mean, there's products in the market you can do analysis on your partitioning concept, for example. But there's no product from EB.
Okay. We've had somebody ask, can I rely on safety features of EB Auto Core for ASIL D applications such as steering, or only for ASIL B?
Actually, the Auto Core, so if that question refers to the ASIL B ready package, you can only rely on up to ASIL B. If you have a system which has an integrity level higher than B, C, or D, and steering basically would be probably a D, you can rely on the safety product. So there's not the Auto Core, it's the OS, Timey, E2E, and the safety RTE.
And is your solution ASIL D fail operational? Consider a 2 ECU solution with 1 controller per ECU, for example.
So fail operational is a good point, right? Here, I think it can be used within a fail operational system, given that there is enough redundancy. So it can be designed that way. So it's a system design issue in that case. So there's nothing you can purely put on a safety element out of context. So I don't think that this will ever be possible, right? You have to guarantee some redundancy within your hardware.
And what would be the effect on the ECU if safety measures failed?
Actually, so the safety measures like memory protection, they should not fail. That's the reason why they are rated like that. So if they fail, right, you have a serious problem, right? Because that is the reason why you take these measures. It has some severe impact on the execution of the system. In the vehicle, right, worst case would be an accident with some terrible damage.
This is a follow-up to the fail operational question. Can you run software on both ECUs to achieve ASIL fail operational solution?
Yes, you can execute them on both ECUs. Of course, you need to think about the diversity of your software, right? If you think about how different you do your fail operational system, right? Maybe you choose different suppliers, maybe different application developers as well to do a redundant system. And I think there's a lot you could learn from the avionics industry because they actually used to do fail operational systems which are highly redundant, also with voters, and to take a decision based on multiple inputs. But yeah, technically it is handled as two different binaries basically, and you could use our products also on the two different micros.
Here's an interesting question. Has there been an independent functional safety assessment on your product EB AutoCore?
Not on the AutoCore, not yet. No, we have on the safety products. There is a certification done by Exida. The report is also publicly available, and yeah, but not on the general product.
So can you please provide some outline of how you perform safety analysis on a software component that's been developed as an SEOOC?
Okay, yes. Yeah, so basically you do a hazard and risk analysis on your function or your requirements on your system, and basically go derive your measures and your software requirements from this hazard and risk analysis, and then implement. Basically, for a safety element out of context, you need to take certain assumptions on the system, on the environmental on the environment, and so basically you need to document them. This is something which goes into the safety manual, and and then you do also, based on these assumptions, you derive requirements, and then based on these safety requirements, you implement your system or your software.
Okay, I think we've got time for one more, a fairly long question, but I think it wraps up nicely. When we do the development of a software component which is meant for higher ASIL, do you recommend any tools in the market which can help validate or confirm the safety considerations even of the software component? Is there anything that you use in particular?
I will not recommend one here. I think there's multiple tools available in the market. So whoever sent the question, you can reach out to us directly, and then we can talk about that separately, because there's multiple products, and then, so they have all their advantages and disadvantages, and it needs to be discussed on a case by case, I would say. So whoever sent the question, please get in contact with your sales representative, and then we can find out how we can help you there.
Sure. Okay. Well, I think that's a good moment to wrap up, Roman. Thank you very much for sharing your insight with us today. Thank you to Elektrobit for helping to make this particular webinar possible, and thank you, of course, to everybody who attended. We will be sending out an email in the next 24 hours to let you know how and when you can access slides and an on-demand recording of the webinar. And with that, I would like to thank you all again and wish you a pleasant day. See you at the next Automotive World webinar. Goodbye.